All right, let's talk about the AI race. Because honestly, it feels like every single week there's a new AI model dropping. Garlic, Opus 4.5. The names just keep coming and the announcements are getting faster and faster. It is a relentless, high-stakes race. But what is really going on behind all the hype and the headlines?
This comment from a recent online discussion really just cuts right to the heart of it. Are we actually witnessing genuine, groundbreaking progress here? Or is the whole AI industry just caught in this frantic numbers game, this battle to be number one on the leaderboard?
And this is the world it's all happening in. It's this chaotic whirlwind of weekly model drops, endless benchmark showdowns, and these fiery online debates. You hear insiders talking about code red situations, while users are calling brand new releases dumpster fires. And the whole thing is just being supercharged by billions and billions of dollars in investment, pushing the race to go even faster. But to really understand what's going on, we have to pull back the curtain on all that hype. We need to start with the first major reality check, the absolutely staggering cost it takes to power this race. Because let me tell you, building these models is anything but cheap. So why is it so expensive? Well, it all comes down to this thing called token-level training. Think of a token as just a tiny piece of a word. These models learn by reading text one tiny token at a time, and then trying to predict the very next one. It's kind of like trying to learn a new language by reading the entire dictionary word by word. It's incredibly detailed for sure, but as you can imagine, it is brutally slow and just eats up a massive amount of computing power. And look, this isn't just some small hiccup. The researchers themselves are calling these costs a significant bottleneck. The sheer expense of training these things is literally holding the entire field back from what could be the next generation of AI. So how on earth do you solve a problem that big? Well, you solve it with some absolutely brilliant engineering. There's a new method called patch-level training. So instead of going token by token, this method groups, let's say, 4 tokens together into a single patch. The model then learns to predict the next patch. It's like reading a book by skipping from one chapter summary to the next instead of reading every single word. It is way, way faster. And the impact is just huge. This one innovation can slash the overall training costs by half. We're talking a 50% reduction without any real drop in the model's performance. That's not just a tweak. That is a total game changer for making this whole AI race financially sustainable.
Okay, so engineering can make training cheaper. Fantastic. But even if we can afford to build these massive models, it brings up a much more fundamental question. Can we really achieve progress just by making them bigger and bigger? Or are we about to slam into a scaling ceiling?
To get this, we've got to talk about something called the signal-to-noise ratio. Just picture you're trying to tune an old analog radio, right? You're twisting the dial, trying to find that clear music, that's the signal. And you're trying to get rid of all that static and hiss, that's the noise. Well, in an AI model, the signal is the useful pattern it's learned, and the noise is all that random internal confusion.
Now, here is where things get really fascinating. The most powerful abilities in these AI models, things like complex reasoning, they don't just get a little bit better as the model gets bigger. No, they don't appear gradually at all. They seem to just switch on, appearing almost out of nowhere. And the reason is, they only emerge once that signal becomes strong enough to completely drown out the internal noise. The moment that signal-to-noise ratio crosses a very specific, critical threshold, boom. A new skill, like advanced math or coding, it just activates, like a light switch flips on. But, and this is a huge but, here's the massive catch. Unlocking each new major capability requires an exponentially bigger model and an exponentially larger dataset. This creates this brutal law of diminishing returns where every new breakthrough is just astronomically more expensive than the one before it. And this all leads us to the deepest challenge of all. I mean, beyond performance and cost, we have to ask a more philosophical question. Can these machines actually think in a way that is logical, reliable, and provably correct? And this gets to a really fundamental difference. An LLM works on what's called stochastic plausibility. It's basically a hyper-advanced pattern matcher, a professional guesser. It generates what sounds statistically likely to be the right answer. On the other hand, you have a formal system, like your calculator or chess engine. It uses formal logic. It doesn't guess. It follows a strict, provable set of rules to guarantee a correct answer every single time.
As the AI researcher Alejandro Piar-Morphis puts it, these LLMs are designed from the ground up to approximate correctness with plausibility. They are built to generate convincing text, not to be mathematically certain. Their whole goal is to sound right, not necessarily to be right. So you end up with these core, baked-in limitations. Their probabilistic nature means they can always be wrong, just by random chance. They have no separate, reliable way to double-check their own work. And this is crucial. They spend a fixed amount of thinking time on a problem based on how long your question is, not on how difficult the problem actually is. So where does that leave us? When you put it all together, the hype, the clever engineering, these deep scientific limits, what does the state of AI actually look like today? I think this user, Yaboy Young Airvent, just captured it perfectly with this metaphor of a jagged frontier. AI progress isn't some straight line moving ever upwards. It's jagged. For your specific needs, a model might not get any better for years, while at the same time it's making these huge leaps in areas you never even use. So, this gives us a really clear picture of the modern AI development cycle. It all starts with the hype and the race to top the benchmarks. Then, clever engineering comes in to make that race affordable. But pretty soon, progress smacks into the wall of scaling limits. And all the while, these deep, fundamental gaps, like true reasoning, they remain.
So if there's one single thing to take away from all this, it's this. AI progress is not a smooth, steady climb. It's messy. It's a series of absolutely stunning breakthroughs in some specific areas, right alongside these deep, persistent, and maybe even unsolvable roadblocks in others.
Which, of course, leaves us with a final, critical question. If simply making models bigger isn't the answer, and if just chasing benchmarks has its limits, what does the next truly revolutionary breakthrough in artificial intelligence even look like? And where is it going to come from?
Thanks for watching. Don't forget to like, subscribe, and share. It really helps the channel grow. See you in the next video.